Okay, so this is my lecture plan, and last time we started with lecture 1. Now, as you can see, the download bar is going rather slowly. And so we ended up here in the middle of section 4. And what we're aiming for to finish lecture 1 is Dyson's threefold way. But let me remind you quickly what we did last time, since you're being bombarded with a great deal of material. So we started with a general discussion of states and projectors and Wigner's theorem, which ultimately told us that there's a kind of universal set of potential symmetries of a quantum system given by the group of unitary and anti-unitary operators on Hilbert space. What's actually realized in this system is a phi-twisted central U1 central extension of a group G. So remember that a group is Z2 graded just means that there's a homomorphism from G into Z2. Sorry, Nadi. Let me try and make it bigger. And then we reviewed some linear algebra, and then we were discussing the representation. Different color. Okay. Fussy audience here. Yeah. I mean, you actually want to see it. Okay. So that's what a Z2 graded group is. Remember that a representation has unitary operators for phi equals +1 and anti-unitary operators for phi equals -1. And then we were finishing up with Schur's lemma. How's that? Clear? Bigger. Oh, my God. I'm spending half my time erasing. Okay, so we ended up with Schur's lemma, which, remember, it said that the space of C-linear G invariant maps from V to V, where V is an irreducible G phi representation, which I'll also write as the endomorphisms of C-linear endomorphisms, which are G invariant. That's just notation. Is a real division algebra. And remember, that's an algebra where every non-zero element is invertible. And then I quoted a theorem of Frobenius, which says that there are exactly 3 associative real division algebras: the reals, the complexes, and the quaternions. And I finished by giving some examples. So now let's take it up from there. Are there any questions from last time? Alrighty. So the next topic in section 4 is complete reducibility. So here's the theorem. Suppose G is compact, then any, I suppose, finite dimensional G phi rep is completely reducible, meaning the following. You make a list of the distinct, but a complete list of the distinct irreps of G phi. Okay? And then if you have any representation V, you can write it as a direct sum over these irreducible representations of a degeneracy space tensor the irrep itself V lambda. So the idea is that G is acting by unitaries and anti-unitaries here, and if I make this isomorphism, then G just acts by the irreducible representations here, and it acts as the identity here. So this S lambda is a real vector space, and it's just representing the degeneracies. Now, some people have a little trouble when I say things this way. They don't know what these funny circles with pluses and crosses mean. So let me just remark that this is just another way of saying that we have block diagonalization. So we could choose a basis such that rho of G has blocks corresponding to the different representations. And inside this block here, we have a matrix that's a tensor product. Little s lambda will be the dimension of capital S lambda. It's a real vector space. Tensor rho lambda of G. Okay, and what that means is that we have another block where we have exactly the same matrix, rho lambda of G, and so on. S lambda times. There are little s lambda blocks. Okay? So that means that by sure, the operators that commute with the group operators they can rearrange the blocks because these are all the same, and they can also be matrices within the blocks that commute with rho of lambda, but since V lambda is an irreducible representation, that has to be a real division algebra. And so what we can say then is that the intertwiners, the space of intertwiners of V with itself, is a direct sum over lambda of arbitrary matrices on this vector space of degeneracies, tensor the intertwiners on V lambda. But you see, by Schur's lemma, this is, for each V lambda, this is a particular real division algebra, R, C, or H. I'll call it D lambda, the division algebra associated with V lambda. And so this is just equal to matrices over D lambda. Now let me say the same thing in terms of algebras. It will be a useful point of view. So I'm just going to repeat myself by rephrasing it in a slightly different way. So let's let rho of G be the algebra of operators generated by the row of the individual group operators. And so that's a subalgebra of the endomorphisms of V. And let's then we can interpret this thing here as, I'll denote it as Z of V rho, as the commutant of rho of G inside this algebra of all operators. Actually, I've made a mistake in my notes. It should be VR. And I should also include multiplication by I. Multiplication of I and rho of G. So remember, V is a complex vector space. That's the definition of a G phi representation. And so there is a notion of a linear transformation I. Okay, now here's some notation which is useful. If K is any algebra, then I'll let K of M be, by definition, it's just notation, the M by M matrices over K. And I'll let M times K be the algebra of matrices which are diagonal with the same element on the diagonal, okay? So such that little k is in big K. And so this, of course, is isomorphic to K, but it's a subalgebra of K of M. So then we have a very beautiful theorem of Weil. Seems like all the theorems here due to people at the Institute. So Weil says that this algebra, rho of G, has a decomposition in terms of little s lambda, d lambda of tau lambda. I'll define tau lambda in a second. And then the commutant of V in rho is, rather beautifully, isomorphic to tau lambda, d lambda opposite of s lambda. So what's tau lambda? Tau lambda is twice d lambda if d is r, d lambda if d is c, and d lambda over 2 if d is h, where d lambda is the complex dimension of v lambda. Okay? So this is really another way of saying that the algebra generated by the group operators will make a complete matrix algebra for each of the irreducibles. And then the things that commute with them, as I said, are the things that rearrange the degeneracy blocks. Okay, so let's see. So I didn't leave myself much space. I have a little space over here. So one little remark which might be helpful to some people is that complete reducibility, I stated it for compact groups, but complete reducibility can apply for non-compact groups. So for example, for crystallographic groups, those are infinite groups, hence not compact. Nevertheless, this will apply. So for example, if G is just a lattice in Euclidean space, then this is Bloch diagonalization, but that's Bloch with an H. You see, this sum over lambda just becomes a direct integral over the irreducible representations in the Brouwer torus. So this is so Bloch's theorem is a special case of this applied to crystallographic groups. All right, so that completes section 4 of the outline there. Oh, the audio guy told me not to do that. That completes section 4. And now I want to talk about quantum automorphisms compatible with a group action. So I'm deliberately not using the word symmetry because the word symmetry means many things to many different people. It's a very mixed term. And so I will define what I mean by compatible with a group. Some people object to what I'm going to define as something that should be called a symmetry. But I think what I'm going to define is a well-defined concept. All right. So we saw in section 1 of lecture 1 that groups in quantum mechanics preserving probabilities automatically come with a Z2 grading, ultimately telling us whether operators are realized linearly or antilinearly. But let's observe something else. In physical situations, if we have let me call it a symmetry in quotes, then we have to decide, is it going to preserve or reverse the orientation of time? It's a basic choice we need to make. So in physical situations, we automatically have a second group homomorphism, tau from G to Z2, telling us whether we preserve or reverse the orientation of time. Now let's suppose, for simplicity, that our system is time translation invariant. And then unitary evolution is generated by a self-adjoint Hamiltonian. And we define G phi to be compatible with the dynamics determined by our Hamiltonian if rho of G times U of T times rho of G inverse is U of tau of G T. In other words, if our symmetries, in quotes, preserve the orientation of time, then we certainly want these operators to commute with unitary evolution. And if they reverse the orientation of time, then they should take the evolution backwards in time. Now, as a tiny exercise, a one-line exercise, I encourage you to show that this means, for the Hamiltonian, that rho of G, H, rho of G, inverse is chi of G, H, where chi of G is phi of G, tau of G. How does that come about? Well, you bring the conjugation up into the exponential, and then you have to bring the rho of G past the I, and that gets an extra plus or minus sign from the phi, and you equate it to this, and you get this formula. So that means there are actually three group homomorphisms in play, but really there are only two because we can get any third guy from the first two. So which two appear as primary in our physicals problem depends on the setup. General principles, whichever two you take, general principles of quantum mechanics imply that a symmetry group is always Z2 times Z2 graded, unless you're doing something like quantum gravity with a time non-orientable space-time or something very exotic like that. What phi is? Remember that in section, I said 1, I meant 2. In section 2 of lecture 1, we determined that any group, remember I drew a big complicated commutative diagram, which I'm not going to draw all of, but G bar was our a priori system of symmetries of our system. It pulled back to G, which was mapping into the real automorphisms of our Hilbert space. This had a homomorphism to plus or minus 1, telling us whether it's unitary or anti-unitary, and I'm also using phi for the composition there, so it's just telling us whether group elements are realized linearly or anti-linearly. Okay, so that's what phi is. Are there any other questions? Yes? I don't understand that question. Some operators will reverse the sign of t and the others won't. I mean, we could You see, we could work with an anti-Hermitian operator as the generator of time translations and erase the I here. But we'd still end up with a Z2 times Z2 graded group. I mean, we started just by observing that any operator has to reverse or preserve the orientation of time. So I could rephrase this in terms of anti-Hermitian generators of time translation by putting the I and the H. But tradition demands that we separate out the I from the H. Any other questions? Okay, so we have this general lesson that, oops, there goes an eraser. Tradition demands that we, so we have general principles of quantum mechanics which tell us that a group is always Z2 times Z2 graded. Now I want to make 5 remarks about this. Remark number 1. If chi of G is -1 for some G, okay, then clearly we have something funny going on. We have a Hamiltonian reversing, quote, symmetry. People sometimes object to that word. That's why I said groups compatible with the dynamics. What it means is that the spectrum of the Hamiltonian is symmetric around 0. Now, you see, in condensed matter, there's no natural 0 of the energy. You could always add a constant to your Hamiltonian. But if you have this kind of operator in your theory, then 0 does really mean something, and the spectrum is symmetric around 0 because a group operator with chi equals -1 will take every energy eigenstate of energy E to one of energy minus E. Which leads me to remark 2, which is that suppose that H is bounded below and not above, for example, the Schrödinger operator in a crystal, or your typical relativistic quantum field theory, then chi must be equal to 1. Right? Because you can't have this symmetry if H is bounded below and not above. And so, indeed, all of the quantum mechanics texts that I've consulted say that chi is 1. They say that a symmetry is anti-unitary if and only if it reverses the orientation of time. Nevertheless, there exist physically interesting systems with chi not equal to 1. Chi equals 1 means chi is trivial. It means chi of G is 1 for all G. Chi not equal to 1 means chi is non-trivial. It means chi is -1 for some G. That is, there could be antilinear, quote, symmetries that preserve time orientation. And Charlie Kane, in his first lecture, mentioned one with polyacetylene, some chiral symmetry, and Andrei Bernovig mentioned one yesterday. And for the moment, however, we take chi equals 1, indeed, and that will lead us to Dyson's threefold way. And then when we relax this constraint, we'll get to the tenfold way.
Excuse me, Greg.
Yeah.
The examples where chi wasn't 1 were the examples involving the Bogoliubov Dijon Hamiltonian?
That was one set of examples, and polyacetylene, if you consider that also in the Bogoliubov Dijon class. I don't quite think that's right, but the polyacetylene that Charlie mentioned, he stressed that he also said it was artificial, and it's not true. It's not there in real acetylene. Yes, sorry. Yes, that's true. But it was anti-commuting with the Hamiltonian, and that's the point I'm stressing right now. Okay, so we're going to take, for the moment, we're going to take chi equals 1. And then we're going to relax it. Now, remark number 4. So we have, back to chi equals 1, with time orientation reversal or not, we have this homomorphism. It has a kernel. Let's call it G naught. And unfortunately, a lot of people seem to assume that this implies that G is G naught times Z2, or maybe G naught is the semi-direct product of Z2. When this happens, the sequence is said to split. That's a split sequence. But not all relevant groups in condensed matter have a split sequence. In fact, in condensed matter, it's called a non-symmorphic magnetic crystallographic group. You see, there are 230 3D space groups, and there are 1,651 3D magnetic space groups. Okay, why are there more than 7 times as many? Well, because you can have this phenomenon where you have different extensions by Z2.
Sorry.
Yep.
Is there something, so you said if H is bounded by below or above in a symmetric way, is there...
No, I said if H is bounded below and not above, then chi must be equal to 1. If H has a finite spectrum, then chi can be, even if it's an infinite spectrum, but it has to be unbounded below. So I'll give some examples later. Okay, last remark, and that's really for the experts, is when you're discussing band structure with magnetic crystallographic symmetry, you need a double cover of the magnetic point group. And you might ask yourself, and it's something I've wondered about many times, should that double cover be in pin plus or pin minus? And I would argue that it has to be in pin plus, and I'd be happy to explain that later to people who care about such things, but it would take about 10 minutes, so we're certainly not going to do it now. Okay, we are now set up to do Dyson's threefold way, number 6 there. So, as I said at the very beginning of my first lecture, usually we start with a Hamiltonian and we find the symmetries. And Dyson turned that around, so I'll call this the Dyson problem. Given a G phi representation, not necessarily irreducible, just a G phi representation H, what is the ensemble of compatible Hamiltonians? And as I said, we're all set up to solve this. H is going to be completely reducible. We're assuming chi is equal to 1. So H has to be in the centralizer of the group algebra. So that's isomorphic to matrices S lambda by S lambda over the real division algebra that we associate to V lambda. And H has to be Hermitian. Well, the division algebras have a conjugation, so it makes sense to talk about the Hermitian S lambda by S lambda matrices over D lambda. And that is the answer. Okay? And it's called the threefold way because the basic ensemble is Hermitian N over D, which is just real symmetric for D equals R, Hermitian for D equals C in the standard sense, and quaternion Hermitian for D equals H. Now, each ensemble has a natural U and D invariant measure. And if we ask that the matrix elements be statistically independent, then there's more or less a unique choice. So, for example, for the ordinary Hermitian operators, that measure looks like this. And the other two are similar. And so then we can diagonalize Hermitian matrices, factor out the volume of the unitary group we're not interested in, and get an eigenvalue distribution, a probability distribution on the eigenvalues. And that's going to look like this. Where beta is the real dimension of the relevant division algebra. So beta is the dimension over R of my division algebra. In other words, it's 1, 2, and 4. Okay, so you see that because of that beta, we're going to have different kinds of statistics. Now, before we move on to lecture 2, maybe I should pause and just say, put this in a little bit of context. So, as I also mentioned at the beginning of lecture 1, this originated in nuclear physics, where people were trying to describe resonance lines associated with scattering of slow neutrons off heavy nuclei. It entered, as far as I'm aware, into condensed matter physics in the 1980s. Now, I'm not an expert on this subject at all, so my understanding from review articles is that it entered in the 1980s in the subject of what's called mesoscopic physics. So what's mesoscopic physics? Well, that's physics at a length scale bigger than an atomic scale, but where quantum interference is still important. So roughly speaking, something that's bigger than a virus and smaller than a bacterium. Okay, and a good example of what of where random matrix theory entered is the phenomenon of universal conductance fluctuations. So if you take a very small, a mesoscopic size, a gold ring or a silicon MOSFET, and you measure the conductance, so you model this by electron transport in a disordered medium, and then there are reproducible fluctuations on the scale of E squared over H. And they seem to be independent of the length of the sample, I believe also of the amount of disorder, and a reproducible function of the magnetic field. So people made sense of that universality by thinking about random matrix theory. Now, later in the 1990s, there were three developments. One was Barshat was studying the statistics of the eigenvalues of the Euclidean Dirac operator. Now you see the Euclidean Dirac operator has this kind of structure, some kind of chiral symmetry, and he found that the statistics was not well modeled by that up there, and he needed a new distribution. Outland and Cernbauer were studying, again, electron transport in hybrid systems, metals with superconductors, hybrid systems, metals and superconductors, and we're finding the need for other statistics. And then here in Princeton, two mathematicians, Nick Katz and Peter Sarnak, were studying the statistics of zeros of L functions. And L functions are things in number theory which generalize Riemann zeta functions. And again, they found that there was some need for a broader class of ensembles. So this culminated in the Outland-Cernbauer, which is really proved by Heinzner-Huckeldarian-Cernbauer tenfold way, which is going to be our aim. Around 2008, Andreas Ludwig and collaborators and Alexei Kitaev then applied some of the same mathematics to make this famous periodic table of the topological conductors and insulators, and that's why I'm talking about it in this school. All right, so now we're on to lecture 2. And I want to begin lecture 2 by mentioning what kind of physical systems might have chi not equal to 1. So now we're going to relax the constraint of chi equals 1. Yes. Well, that would take a little bit of time. So what you need to do is you need to write H equals U lambda U dagger, where lambda is the diagonal matrix of eigenvalues. Then, yes? Okay, and then you need to make a change of variables. Okay, this is a change of variables. It's a change of variables, so you really have a map from un mod u1 to the n times real diagonals to the Hermitian matrices. And you need to calculate the Jacobian of that map, which might make you a little bit scared, but you shouldn't be scared because you just take the unitary operator to be 1 plus anti-Hermitian, okay? And you work the first order in epsilon, and then you'll calculate the Jacobian, and it will turn out to be this product here.
Sorry,
What's
what's beta there?
lambda I minus lambda j to the beta. Beta, remember, we have 3 different basic ensembles, and beta is the real dimension of D, so it's 1, 2, or 4 in the 3 cases. And so that makes a big difference to the statistics. Yeah, I don't know what to make of that. It's been noticed before. I don't know, there are a lot of experts in the room. Is there some deep reason for this? No. Okay. Well, that's the voice of authority speaking. So,
I have a quick question about symmetry around 0 of the spectrum.
yep.
If you displace the Hamiltonian by a constant, you break that symmetry, and I always thought displacing by a constant should really do something that rapid.
Well, that determines, that's a chicken-egg problem. If you think that you have some kind of symmetry that's fundamental, then you aren't allowed to add such terms. I mean, that's sort of a standard thing. If you want to postulate a symmetry, then you constrain your Hamiltonians. You could have said the same thing about the threefold way.
But is there a more general definition by saying, like, there exists a constant which I can add to my Hamiltonian such that the resulting Hamiltonian...
Yeah, good question. Good question. So, I'm actually, that's going to be part of what I'm about to say. So now we're moving on to the tenfold way, and I want to say something about potential realizations in physical systems. So this is number 1 on lecture 2. So the primary example, to be sure, is free fermions. Okay, so in free fermions, as I'll write again later, if time permits, we have a Hamiltonian, which is I times Aij EI, EJ. EI and EJ are the Majorana modes, and A is a real antisymmetric matrix, and that'll be a fundamental formula for what I say later. But this will sometimes, depending on A, will admit systems with chi not equal to 1. Now, about your question of shifting the Hamiltonian, well, sure, if you have some energy, say in a gap in an insulator, and you just have a few bands, okay, you might have a symmetry just for those few bands near the insulator, near the Fermi level, right? Okay, then if you wanted to emphasize this symmetry and forget about the fact that actually the Schrödinger Hamiltonian is unbounded above, you're just concentrating on an effective theory of some bands near the Fermi level, then you would shift your energy so that this was the zero, if you wanted to emphasize that symmetry. So that's the answer. So what are other possible? So there are other possible realizations. The question, which I don't know the answer to, is how natural do you want to think that these examples would be? So let me mention some. So we could have a bipartite lattice. Okay, and then you could take an Ising model, or you could take interacting fermions, and you can write Hamiltonians on a bipartite lattice where you're exploiting that bipartite lattice to get these kinds of E to minus E symmetries. There's also an interesting paper in the literature that suggests that there are applications to photonic band structure. At least I found it interesting. It's a paper by Donitis and Lane. However, I was at a workshop in Vienna last year where there were some experts in the audience who were highly critical of this work, so I'll put a question mark there. I'm not myself sure if, but I think it's actually quite interesting if it could be applied, because of course photons are not fermions. Along the same lines, you can certainly, theoretically, you can engineer phonon band structures. And whether or not that can be realized in real physical materials, I do not know.
So how can aren't those bounded below?
Well, I mean, you can have a finite number of phonon bands, right? So that's how you get out of that. So you have to get rid of the acoustic mode. So you glue it to something. And last but not least, the Hilbert-Polya Hamiltonian, whose eigenvalues are equal to the zeros, the non-trivial zeros of the Riemann zeta function, if it exists, would of course have this kind of E to minus E symmetry. So if there really were, as some people try to claim to me, a theorem that any interesting example has to be free fermions, then that's interesting to the number theorists because it means that the Hilbert-Polya Hamiltonian, if it exists, must be some weird Dirac operator on some weird space. Okay, so now the way we're going to understand these chi not equal to 1 systems is in terms of Z2 graded or superlinear algebra. So I'm now going to dive back into mathematics. Are there any questions before I do that? All right, okay. So let's talk about some mathematics. So now, what is a super vector space? That's easy. A Z2 graded and super in the math literature are completely synonymous. So a super vector space over kappa is simply a vector space over kappa with a decomposition into two subspaces, a direct sum of two subspaces, which are called the even and the odd subspaces. And homogeneous vectors are vectors which live entirely in V0 or entirely in V1, and they have a well-defined degree, which I'll also write as V absolute value, which is either 0 or 1, thought of additively mod 2. So example 1, suppose that V has an operator gamma, which squares to 1. So for example, gamma might be minus 1 to the f in a theory with fermions. Then the even fermion number space would be the even space, and the odd fermion number space would be the odd space. Example 2. Suppose that we have a real vector space, V, with a complex structure. Then the endomorphisms of V, the real endomorphisms of V, has a Z2 grading. Because, you see, I can take an operator and I can conjugate it by I. Okay? So if you do that twice, because I squares to minus 1, which commutes through, this is a Z2 grading. Example 3. It's really more of a definition than an example. Supposing that kappa is C or R, or really any field, then kappa to the n plus slash n minus is by definition the supervector space with, this is the even part, this is the odd part, and n plus slash n minus is called the superdimension. Okay, so now let's see, visible. So now supposing we have two supervector spaces, then the set of all linear transformations from V to W, V and W are supervector spaces. I claim that is itself a supervector space in a natural way. The even part is the linear transformations from the even to the even, and the linear transformations from the odd to the odd. And the odd part is the linear transformations from the odd to the even plus the linear transformations from the even to the odd. So if I choose a basis of homogeneous vectors, then the matrices in that basis for even operators will look like this. So this is even. And the matrices of the odd operators will look like this. And I will always choose bases of homogeneous vectors. Now we can also speak of a superalgebra. A superalgebra, A, is first of all, a supervector space over kappa with a kappa bilinear map, the multiplication, which is an even map, meaning that the degree of A times A prime is the degree of A plus the degree of A prime. Now remember, those are integers modulo 2. And here I introduce an important convention. Whenever I write a formula with degree in it, it is understood that the vectors in question are homogeneous, so the formula makes sense. Now, along those lines, two elements are said to graded commute if A prime is A prime times A prime A, and that minus sign is significant. So this is graded commute. the supercenter of my algebra is the set of elements whose homogeneous parts graded commute with all other homogeneous vectors. AB is equal to minus 1 to the A, B, BA for all B in A. Now, every superalgebra is, of course, an ordinary ungraded algebra, and the supercenter might or might not be the same as the ordinary ungraded center. You have to keep your wits about you when you're doing superalgebra. Now, one important thing you can do with superalgebras is you can take the graded tensor product. So, first of all, the tensor product of supervector spaces is a supervector space in a more or less obvious way. It's a formula very much like what I just wrote for the hum between two spaces. For the graded tensor product, let me see if I could squeeze it in here. A1 tensor product, and the little hat on top means it's the graded tensor product, is first of all a supervector space in a natural way. And the important thing is that the way I define the multiplication of the tensor product of homogeneous vectors is I use what's called the causal sign rule. So this is A1, A2, tensor hat, B1, B2. That sign rule there is called the causal sign rule, and it can have dramatic consequences. So what's an example of a superalgebra? If V is a supervector space, then the linear transformations of V to itself is a superalgebra. Okay? Because, you see, because the product of an even and odd matrix, you see, still is off diagonal, so it's odd. And the product of odd with odd is diagonal, block diagonal, so it's even. And that's all you need to check. Now, this is called a matrix superalgebra. And the important point is that not all superalgebras are matrix superalgebras. That is the concept of Morita equivalence. Now, the proper way to define Morita equivalence is to say that two superalgebras are Morita equivalent. A1 is equivalent to A2 if their representation theory is the same. Technically, if there's an equivalence of categories of representations. But we don't need that. All we need to know is that these will be Morita equivalent if one is a matrix superalgebra over the other. In other words, if A1 is A2 tensor hat and automorphisms of V for some vector space V, or the other way around. So that's all we need to know. Think of Morita equivalence as just saying that one is a matrix superalgebra over the other. Question?
If one is a matrix superalgebra over the other, can you make any statement about A2 being a matrix superalgebra?
No. The equivalence is that either one, that A1 or A2 goes this way. Now, you can define, let's call the equivalence classes A1 with a bracket like that, and there's a well-defined multiplication where I take the graded tensor product and I take its equivalence class, and this multiplication might or might not have an inverse. So now we move on to number 3, to the very significant example of superalgebras given by the real and complex Clifford algebras. Are there any questions? Okay, so now we're doing real and complex Clifford algebras, and let's start with the complex Clifford algebra, CLN. It has n odd generators, E1 through En, and they satisfy the usual relations, EI, EJ, plus EJ, EI, is 2 delta ij. Or I could take minus 2. Why could I take minus 2? Because we're working over the complex numbers. I could equally well have multiplied all the e's by the square root of minus 1. And then I'd get a minus 2 on the right-hand side. Okay? So that's just a convention. However, when I look at the real Clifford algebras, which I'll denote this way, with a straight C without the blackboard bold, okay, that's again going to be an algebra with odd generators generated by E1 through En. And for n positive, they're going to satisfy exactly the same relations. But now, you see, there's another real Clifford algebra, Clifford minus n, where again I'm going to have n odd generators, but I'm going to have ei ej plus ej ei is minus 2 delta ij. Okay? And this is, in general, a different algebra. I can't get rid of the minus sign because these are real algebras, so I'm not allowed to multiply by the square root of minus 1. All right, so as a little exercise, I invite you to calculate the super dimensions of the real and complex Clifford algebras. Anybody want to tell me the answer? Does anybody know? Let me actually write it. Here, I think I can squeeze it in. Oh. Okay, so the dimension over the complex numbers of CLN is 2 to the n minus 1 slash 2 to the n minus 1. And the dimension over R of CL plus or minus n is 2 to the n minus 1 slash 2 to the n minus 1. Okay, and I leave that as a tiny little exercise. So you see you can make words out of the generators EI, but think of them as occupied and unoccupied fermions, for example, Myron or complex fermions. And so you only have 2 to the n total possibilities, and it's equally, so half of them are going to involve an even number of generators, and half of them are going to be an odd number of generators. So I said the generators EI are odd, and so I then have a Z2 graded algebra according to whether an element is obtained by multiplying an even or an odd number of Clifford generators. And that's consistent because the relations here only involve an even number of generators. So now, in terms of these graded tensor products, these Clifford algebras can all be reduced to one dimension. So in terms of the graded tensor product, we can write this. And similarly, Clifford n is Clifford 1, tensor hat Clifford 1. And Clifford minus n is Clifford minus 1, tensor hat Clifford minus 1. So what's all the fuss about Clifford algebras? Looks pretty trivial. Well, one thing is that, you see, the graded tensor product is not respected by matrix representations. If you have a matrix representation of two superalgebras, the tensor product of the matrix representations is not a representation of the graded tensor product of the algebras, precisely because of the causal sign rule, long erased. But that's the essential reason. So you can't just take representations of these guys and produce automatically matrix representations of the Clifford algebras. So let's look quickly at the structure of the complex Clifford algebras. So if we take Clifford 0, well, that's by definition C, not much to say there. Clifford 1 is the first one to talk about. So that as a graded vector space is C plus CE. E squares to 1. E is odd. So it has a one-dimensional even piece and a one-dimensional odd piece. And the thing I want to stress here is that this is not a matrix superalgebra. Its dimension isn't even right. Now, this is as far as you can go if you think of it as a graded algebra. As an ungraded algebra, you can introduce the inhomogeneous element P, which is 1 plus and minus E. Okay? And that's a projection operator because E squares to 1. And so as an ungraded algebra, Clifford 1 is isomorphic to C plus C. How about Clifford 2? Well, now we have an irrep on a graded, on a supervector space, C11. We have to represent our odd generators by odd matrices, and we can do that. You see, those two guys are odd, they're off diagonal, and they satisfy the Clifford relations. It would be illegal to put 1 minus 1. You might say, well, that also satisfies the Clifford relations. But that's illegal because it's not odd, it's even. Okay? Now, these two guys will generate the full matrix superalgebra. So Clifford 2 is a matrix superalgebra. But wait a moment. Clifford n is Clifford n plus 2 is Clifford n times Clifford 2. So if we are in the world of Morita equivalents, there are just two kinds. There's the even kinds and the odd kinds, because Clifford 2 is a matrix algebra. Okay, and a tensor product of matrix algebras is another matrix algebra. So I can keep going down, and so now I can make a little table. Clifford 2k, Clifford 2k plus 1. And now we have the graded and the ungraded. And here we have a matrix algebra, C to the 2 to the k minus 1 slash 2 to the k minus 1. If we forget the grading, we just get C of 2 to the k. Here we have that matrix algebra tensor, Clifford 1. And then if we forget the grading, then Clifford 1 is C plus C. And so this is not a simple algebra in the ungraded sense. It's a direct sum of two matrix algebras. So, there are only two Morita equivalence classes of complex Clifford algebras. Okay, moreover, if I take the product of these two, I get back to here. So this forms the group Z2 under that product on Morita equivalence relations. Now, at this point, we are extremely close to a subject known as K-theory, but we're not going there. What we're going to do instead is reproduce this, talk about the analog of this chart now for the real Clifford algebras. And let's see, how am I doing for time? Not too good. Okay. Instead of putting up the chart the way I had meant to, I'm going to tell you a few essential facts. Okay, so we could start this discussion. We could start this discussion just the way we did for the complex Clifford algebras. We could start with Clifford naught, and that's just the reals. And then we could look at Clifford 1. Actually, let's look at Clifford minus 1. Okay, so that's as a supervector space, R plus RE, where E squares to minus 1. As a graded algebra, that's as far as you go. It's an irreducible thing. Okay? As an ungraded algebra, Well, we have a representation, an irreducible representation, where rho of e is the square root of minus 1. Okay, we're violating the grading rule because this is an even number and e is an odd generator. But as an ungraded algebra, we therefore just get c. On the other hand, if we look at Clifford plus 1, then we have this. Now e squares to plus 1. And again, it's an irreducible thing. I can't go further. But as an ungraded algebra, I can do exactly what I did with the complex Clifford algebra. And so I get r plus r. So you see, they're different. They're inequivalent real algebras. Now, you can go your merry way with Clifford plus and minus 2, Clifford plus and minus 3. These are irreducible things. You can't write them as matrix superalgebras. And then something interesting happens when you get to Clifford plus and minus 4. So you see, if you look at Clifford minus 4, then we can represent E1 by 0, I, 0, E2 by 0, J, 0, E3 by 0, K, 0, and E4 by 0, 1, minus 1, 0. All of these square to minus 1, and they satisfy the Clifford relations. And so we get, as a graded algebra, the quaternions times a matrix superalgebra are 1, 1. Okay, so Clifford minus 4 is Morita equivalent to the good old even quaternions. So we didn't get anything new. And if we change the sign here, 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 and here, we get Clifford plus 4 is equal to exactly the same thing. So Clifford plus 4 is Clifford minus 4. This is Morita equivalent to H. So now, because I'm running very short on time, let me just say, I need to do one thing, which is just too beautiful not to do. So now let's take Clifford 4, graded tensor product Clifford 4. Okay? So this is equal to H, tensor, the endomorphisms of the product of the endomorphisms of vector spaces is the endomorphism of the product of the vector spaces. So this is the endomorphisms of R2/2. This, if you did the exercise, is the endomorphisms of R4. It's purely even, so it's R4/0. And so we get the endomorphisms of R8/8. In other words, Clifford 4 times Clifford 4, which is Clifford 8, is Morita equivalent to the ground field. It's a matrix superalgebra. So in the world of Morita equivalence, we go up to 8, and then we're back to where we started. So the result is that there are exactly 8 Morita equivalence classes of real Clifford algebras and 2 of complex Clifford algebras, and 8 plus 2 is 10. Now, I'm not sure if I'm going to get to it, but let me just record what these algebras look like as ungraded algebras. So I've told you that we have a C at minus 1, R plus R at plus 1, and the way you remember what the algebras are as ungraded algebras is you use the Bott clock, or the Bott genetic code, which looks like this. Okay? So this R is Clifford 0. This is Clifford minus 1. This turns out to be Clifford minus 2, Clifford minus 3, Clifford minus 4. You say, wait a second, That's not 8. This Clifford minus 4 is not h. It's h tensor this. But you see, as an ungraded algebra, this thing is just R of 2. So this is the algebra of 2 by 2 matrices over the quaternions. So when I write this, I mean you fill in the appropriate number to make the dimension right. And then it's mod 8 periodic. So you go around this way when you go counterclockwise when you decrease n, and you go clockwise when you increase n. Okay? So if you want to know, question?
No, that's the Bott periodicity.
That's the Bott periodicity indeed. It's closely related to the Bott periodicity. That's the mod 8 periodicity of the real Clifford algebras. And so, if the Sphinx or Turandot or somebody asks you, what is the 65th Clifford algebra? Okay. You see, 65 is 1 mod 8, so you know it's got to be of R plus R. Okay, and so it has to be R of 2 to the 32, direct sum R of 2 to the 32, just from dimensional reasons. So now we're ready to talk about the generalized Dyson problem. Okay. So I have just completed my review of Clifford algebras. So now we return to symmetries in quantum mechanics. And I argued earlier that if we have a group compatible with dynamics, then we actually have a Z2 times Z2 graded group. Okay, so, and I wrote down the formula for compatibility of the group with the Hamiltonian, which I will now write down again to remind you. And the formula is, let's see, I'm not supposed to use blue. The formula is that rho of G, H, is chi of G, H, rho of G. Now, we can look at this formula in many different ways, and I'm just going to discuss one of them. So you might think that you have a Z2 graded Hilbert space, that the operators, the group operators with chi of G equals -1, are Z2 odd, and then you would interpret this as saying that H is in the odd, or the supercommutant, of the group algebra. So now I'm going to write all that out slowly. So, definition. Suppose I have a G phi chi graded group. Okay? In other words, a Z2 times Z2 graded group. I'll say a G phi chi representation is a complex supervector space, V, such that rho of G is, well, it's a phi representation. So it's unitary if phi is +1 and anti-unitary if phi is -1. So we had that before. But now we add that it's even if chi of G is +1 and odd if chi of G is -1. Okay, and so we can state, let's call it the generalized Dyson problem. So given a Z2 times Z2 graded group, and a G phi chi representation, what is the ensemble of compatible Hamiltonians? Okay, so I hope that's a clear generalization of what Dyson asked. And now we are, again, all set up to answer it. And we can answer it pretty much the same way as we answered it before. So just the way we answered it before, I started with a definition of a division algebra. So let's define a superdivision algebra. A is, of course, a superalgebra such that every non-zero homogeneous element is invertible. So what's a good example of a superalgebra? Well, our friend, the first odd complex Clifford algebra, or for that matter, the real Clifford algebras. Same argument is going to work for CL plus 1, CL minus 1. Okay? I claim those are all superdivision algebras. And now why is that? Well, because as a supervector space, it's C, direct sum C times E. So a homogeneous vector lives here or here. Okay? And if it's not 0, it's clearly invertible. If something is not 0 here, it's obviously invertible. If it's non-zero and odd, it's also invertible because E squares to 1. Notice, however, that Clifford 1 and the real Clifford plus and minus 1 are not ordinary division algebras. Why not? Well, you see, I could write something inhomogeneous like 1 plus E. 1 plus E has a 0 divisor. 1 plus E times 1 minus E is 0. So 1 plus E is not 0, and it's not invertible. So Clifford 1 is not a division algebra, but it is a superdivision algebra. Okay. Now, the next step was to look at Schur's lemma. So we have super Schur's lemma. So an intertwiner between, that means we're almost at the end. Okay, I'm going to aim to get to the end of section 4, and then it's a pity about the rest. So we have super Schur's lemma. So an intertwiner between two G phi chi irreps is either equal to 0 or an isomorphism, by which I mean possibly a graded isomorphism. So then, if V is a irreducible G phi chi representation, then the super vector space of graded intertwiners, possibly graded intertwiners, is a superdivision algebra. Okay, so now we do exactly what we did before in Dyson's threefold way. Pardon? Yeah, that's where I'm going. It's an excellent question. the question was, is there an analog of Frobenius' theorem? And the answer is yes, and I will write it in just a moment. So now we make a list of the a complete list of distinct irreducible representations. To each V lambda, we associate a superdivision algebra. And the Hilbert space is, again, a direct sum of degeneracy spaces, times irreducible representations. And now the supercommutant, which is the supercenter of the superalgebra of all linear transformations of H to itself, so there's some extra signs there, causal signs, is equal to the supercommutant. Okay, I just said that's the supercommutant. That is direct sum over lambda of matrix algebras S lambda by S lambda over the superdivision algebras. And then we just had an excellent question. The next step was we quoted the Frobenius theorem, and now I'm going to quote a theorem which is not actually in his paper, but is a corollary of a paper by Terry Wall, topologist. This is a paper from the 1960s. And it says there are precisely 10 real superdivision algebras. And what are they? Well, there are the even ones, the purely even ones. A purely even superdivision algebra is a division algebra, and we have those from Frobenius. I just showed you 3 more. They are not division algebras, but they are superdivision algebras. And now you can check, it's not too difficult, that Clifford plus and minus 2, Clifford plus and minus 3 are also superdivision algebras. So there you have 3 plus 7 is 10. Now you ask, what about Clifford plus and minus 4? Well, remember that Clifford plus and minus 4 was a matrix algebra over the quaternions. Therefore, there's an element in here which is purely even and not invertible. So we're done. And these are the Morita equivalence classes of the real and complex Clifford algebras. Okay, so we're just starting to get to this table here. So the column number 4 is the Morita equivalence classes of the real and complex Clifford algebras. Now it's pretty clear how to complete the story and get if you like the generalized tenfold way. You see, we can put a star structure, so, okay. We can put a star structure on the real superdivision algebras, because they're Clifford algebras, if you like. And so now if we have chi equals 1, we have Dyson. And if chi is not equal to 1, then H is an odd element in direct sum of lambda of the Hermitian S lambda by S lambda matrices over D lambda S. Okay. Now I'm essentially out of time. So let me just sketch what I would have done if I had more time. So I phrased this intentionally in a way that's very general, because as I stressed, it's not clear to me that all of the relevant systems to which this applies should be free fermions. But most of the literature is about free fermions. So the natural question at this point is, how do we relate this to, say, the periodic table of topological insulators and superconductors that you see in the review of Hassan and Kane and Ludwig et al. And Kataev's paper. And so that is supposed to be the content of sections 5, 6, and 7. So let me just sort of sketch what those are about. So if you have a non-trivial Z2 times Z2 grading on the group, let's call it M22 bar, which is Z2 times Z2 itself, okay, then without loss of generality, you can choose generators, let's call them T bar and C bar, such that your Z2 times Z2 grading looks this way. So chi of T bar is +1, so T bar is even. Chi of C bar is odd. And so without loss of generality, you have that situation. Now, I've argued that any group that we have in a physical system has some, I put bars there to stress that that's a grading on this group. So then what we have is a map to a subgroup of M22. Okay? So U is a subgroup of M22. It could be that chi is trivial, for example, or phi is trivial, or they're both trivial. So this will have a kernel, and again, let's make the simplifying assumption. It's not true in general, but let's make the simplifying assumption that G is G naught times U tilde, where U tilde is a phi-twisted U1 central extension of a subgroup U of M22. Okay? So if we decomposed our Hilbert space in terms of irreps of G naught, we would have a degeneracy space here and irreps of G naught acting here. So our phi-twisted U1 central extension of U in M22 would act here on our degeneracy spaces. So it's, in a sense, a kind of universal group. In a sense, you'll always have some C bar and T bar, well, always under these assumptions. Now, how many subgroups are there of M22? Well, that's easy. You make a lattice of subgroups of Z2 times Z2, and you can have the generator, I guess I have it here by C bar, T bar, or of course you could have the diagonal, and then the only other subgroup is the trivial subgroup. Now, if you denote the lifts of C bar and T bar to U tilde, then I proved last time that the lift of T has a square which is plus or minus 1 independent of lift. For exactly the same reasons, the lift of C bar, which I'll call C, has a well-defined sign for its square, and without loss of generality, you can take C and T to commute. So now this describes what I call the 10 CT groups. And the 10 CT groups are listed up there. So this is something like the first 3 columns in your 10-fold way for free fermions. So here, you see, these are in the first column here, we have the various possible subgroups of Z2 times Z2. So we have the trivial group, we have the diagonal group, we have T, we have C, and we have the full group itself. And then I've listed the possibilities for the square of T and the square of C. Okay? So I call those the 10 CT groups. Now, then the question arises, well, how in the world did I decide to assign this pattern of Clifford algebras to it? I mean, after all, just because you see two things with 10 elements doesn't mean that they're the same, right? I mean, you read the literature, and sometimes it seems like they're 10 factorial different tenfold ways in the literature. I mean, I'm fortunate enough to have 10 fingers. Which one goes with my thumb? Okay? So there's a theorem, and I see I'm over time, so I'm going to stop with the statement of the theorem, which says how this goes. Now, it was stated as such in a paper I wrote with Dan Freed, but we were just trying to understand a very cryptic appendix by a nice paper by Fitkowski and Kitaev, which of course in turn was building on Kitaev's paper on the periodic table. And it says that there exists a 1-1 correspondence between the 10 CT groups, call them U tilde, and the 10 Morita classes of real and complex Clifford algebras. And what determines that correspondence? Well, there's a natural equivalence of categories of representations, which in plain English means that to every representation of one of the CT groups, in a very natural way, you can produce a Clifford algebra, and a representation is a graded representation of the Clifford algebra, and vice versa, so that the composition is essentially the identity. And so I'm way over time, so I think I'll stop there.